We begin our study of the basic principles of optimization by looking at a very general form of an optimization problem, which is given by this. Maximize over a variable x an objective function t of x. To provide some motivation, think of the problem as the one faced by a firm that wants to maximize total profits given by t of x. So these are total profits as a function of an action that it can take x, which x is any number. A little bit of terminology. In a general optimization problem, the variable that we can control is called the control variable. And this is the variable that we choose over. And the function that we're trying to maximize, in this case t of x, is called the objective function. Using this terminology, the goal of an maximization problem is to select the level of the control variable that generates the maximum value of the objective function. To provide some intuition, consider a graphical representation of the problem. We have some sort of function, let's say something that looks like this. This is the function t of x. And what we're trying to do is find the level of x in this axis that provides the maximum level of the function. In this graphical representation, this will be this level. Fortunately, there is a recipe that you learn in calculus that allows us to take the function t, apply some derivatives, and find the general value of x star that maximizes the function. And the recipe is given by what are known as the first order or necessary conditions and second order or sufficient conditions. The first order conditions state that any point that is a local maximum must satisfy the condition that its derivative is equal to 0. However, as you probably remember for calculus, necessary conditions are not sufficient. Some points may satisfy them and still not be maximum. And we will see an example of this in a second. However, if a point also satisfies what are called second order or sufficient conditions, which in this case is given by its second derivative is less than 0, then such a point is a local maximum. To warm up and practice what we have just learned, let's do a simple example. Consider the function 10 minus x minus 5 squared. Think of this as the profit function that we are trying to maximize. In order to find the maximum, we need to first apply the first order conditions, which we say that the derivative of the objective function, which in this case is minus 2 times x minus 5, has to be equal to 0. And doing a little bit of algebra, this implies that x at the optimum has to be equal to 5. Now, we know that these conditions are necessary but not sufficient. So let's check the second order conditions, which are the sufficient ones. That requires taking the second derivative of the function, or the derivative of this, which in this case means the second derivative of this function is just minus 2, which is less than 0, which implies that the second order conditions are satisfied and that the unique local optimum or local maximum, and therefore the global maximum, is at x star equals 5. Let me provide you with 3 different types of intuition for why the first and second order conditions look like they do. Let's start with a graphical intuition of the first order conditions. Suppose that you have a function that looks more or less like this. That is the objective function that we are trying to maximize. Remember that the first order condition states that at any local maximum, the derivative at the optimum, at the local maximum, has to be equal to 0. Now, to see why this has to be the case, consider a point, for example, like x, at which the derivative clearly is not equal to 0. In this particular case, it's positive. It is easy to see that the value of the function at that point cannot be a maximum. In other words, x cannot be maximized in the function because given that the slope is positive, if you move a little bit to the right, let's say to a point like x plus delta x, you can increase the value of the function approximately by the value of the slope times delta x. Now, it's also easy to see that if you're at a point like x hat, at which, in this case, the value of the slope is negative, you can also not be maximizing, because if you move to a point like x hat minus dx minus delta x, you can also increase the value of the function for similar reasons. Now, it's very easy to see that the only point at which you cannot play this trick of improving the value of the objective function by changing the value of x is a point like x star at which the slope is 0. Because if you move locally either to the left or to the right, the value of the objective function would not change. This provides an intuition for why the first order conditions have to satisfy this property at a local maximum. Now consider a graphical intuition for why the second order conditions look like they do. To remind you, the second order condition is given by the second derivative at the local optimum has to be less than 0. That provides, together with the first order conditions, sufficient conditions for optimization. Now, to see why that has to be the case, compare the following two functions. The one on the left looks like this, and it doesn't satisfy the second order conditions at the point x star. In fact, it is easy to see that in this case, the second derivative at x star is greater than 0. The slope is becoming progressively more positive as you move to the right. Compare this to a function that looks like this, just like the one before, and at which at x star, our candidate for the local optimum, the second derivative satisfies the second order condition. Let's see why it has to be the case that x star is not a maximum here, but is a maximum here, and the key nature of the difference is captured by the second order condition. Now, if you start at x star in the figure on the left and move a tiny bit to the right by delta x, since the slope is 0, you don't really change the value of the function. So that doesn't help you. However, and this is the key intuition that you have to see, because the second derivative is positive, the value of the slope changes when you move from x star to x star plus delta x and becomes positive here at the new point. That means that if you carry out a further move, let's say by another delta x, since the slope was positive at x star plus delta x, the function now has increased. And that means that by moving 2 delta x to the right, you can improve the value of the function, which means that it cannot be an optimum. In contrast, see what happens if you try to play the same game at x star in the figure on the right. As before, the first order conditions are satisfied, so the slope is 0 at x star. But if you try to move to the right, because, let's say by delta x, because the second derivative is now less than 0, the slope actually goes down and it becomes negative. Therefore, if you try to move a further the x, the value of the function goes down. It should be easy to see, and you should convince yourself that it doesn't matter for these arguments whether the movement is to the right or to the left. In both cases, they go through in an analogous way. This demonstrates the intuition for why the second order condition t double prime of x star less than 0 provides sufficient conditions for the point to be a local maximum. Let's look at the intuition for why the optimization conditions look like they do from a different perspective, in this case a mathematical one. By the way, I'm trying different intuitions because some of you may find some of them more natural than the others. Now, you will recall from basic calculus that the value of the objective function, in fact of any function, at a point x plus dx can be very well approximated by the value of the function at x plus the derivative of the function at x times delta x plus the second derivative of the function at x times dx squared plus a bunch of higher order terms that are approximately 0 for small changes in the value of x. Now, given this, the change in the objective function produced by the change delta x can be written as dt, the change in the function, is approximately equal to the derivative at x times delta x plus the second derivative at x times dx squared. Now, for a function to be maximized at x, it has to be the case that we cannot find a small change delta x, either positive or negative, that increases the value of the function. In other words, that makes the change in the function positive. But notice that if the point x satisfies the first order conditions, the necessary conditions, this term is 0 since the first derivative is equal to 0. Furthermore, if it satisfies the second order conditions, this term is negative. And therefore, the total change in the function has to be less than 0. In other words, when the first order conditions and second order conditions are satisfied, it is not possible to find a small change, a small local change, delta x, that increases the value of the function. Finally, consider the economic intuition for these properties of the maximization problem. Now, recall that we have been thinking of T of x as the total payoff of taking action x, for example, measured in dollars. The profits for a firm, the total well-being for an individual, a consumer. Now, under this interpretation, the derivative of T prime of x, that we're going to call the marginal total payoff of taking an additional unit of the action, given that you have already taken x units, it's going to have a very special meaning. In particular, T prime of x is the increase in total payoff if we increase x by 1 unit, or the decrease in total payoff if we decrease x by 1 unit. It basically gives you the marginal changes that are produced by small changes in your action x. Now, given this, it has to be the case that at the optimum, the marginal total payoff is 0. Why? Think about it. Being at the optimum means that you cannot change your action and do better. But if T prime of x is different than 0, this implies that you can improve by either setting an increase or a decrease in your action. In other words, if the marginal total payoff is not 0, there is something else that is better that you can do better in the sense of improving your total payoff.